All right, welcome back to our Section 1 lesson on describing matter. We tackled the bell ringer on Friday, but I do want to remind you of the 4 objectives that go along with this section first. By the time we're done, you want to be able to distinguish between chemical and physical changes of matter. We talked about those a bit on Friday. Your bell ringer today was about chemical and physical changes again. Remember that a chemical change alters the nature of the substance and its properties, while a physical change is just going to change the way that it looks. Sugar dissolved in water is still sugar, and it can be taken out of that water if the water is allowed to evaporate. The second objective is to identify characteristic properties of matter and explain their uses. So just like with rocks and minerals, every piece of matter has characteristic properties that are going to set it apart from other types of matter that exist in the universe. And understanding the characteristic properties of a piece of matter, help us to use that piece of matter more effectively, and also help us to identify that piece of matter if we encounter it out of context. The objectives we're going to deal with today are the last 2. We need to be able by the end to compare mixtures and pure substances and describe elements and compounds. So there are really 2 general categories of matter. If we want to break it down into like the big picture pieces, matter is either going to exist in the form of a mixture, or it's going to exist in the form of a pure substance. If a piece of matter is existing in the form of a pure substance, we're going to break it down further into 2 subcategories. We'll say that that pure substance is either an element or that pure substance is a compound. And this idea of classification is not new to chemistry. You saw some classification last year when you were studying animals. We had our simple invertebrates and we had our more complex invertebrates. Before we even got to those categories, we talked about living things like bacteria and plants, and it kind of goes on and on from there. But the idea that we're going to classify things into categories with other objects or pieces of matter that are like, it should not be foreign to us at this point. I really like the flow chart that you see on this screen because, as we're going to get to in a minute, we see that pure substances are broken into elements and compounds, but mixtures can be broken into a couple of different categories as well. Now, your book didn't go into a lot of detail on that, but we are going to talk about it sort of in a summary overview today. So mixtures are substances that are mixed together, hence the name. But notice that these are not substances that are chemically combined. So in a mixture, all of the substances involved retain their unique characteristic properties. If you look at the graphic on the screen, you see distilled water, which is pure water, H2O, that's all that's there, in one container, and then in the container on the left you see tap water, and this is exactly the same as what would be coming out of our sinks perhaps at home. It's not just pure H2O when it's coming out of our sink, it's mixed with all sorts of other things, and it would take a bit of doing to get all of those substances separate from one another, but you could. The fluoride in your water retains the characteristics of fluoride. Some of the iron perhaps in your water retains the characteristics of iron, even though it doesn't appear like there are multiple substances existing in that water when you look at it on surface value. Individual substances keep their separate properties. Sometimes mixtures are very well mixed, like this example of tap water. Otherwise, it is very possible to separate mixtures. There are 3 main groups of mixtures. We see solutions, we see colloids, and we see suspensions. Now, mixtures tend to be organized based on how well mixed they are. A solution is going to be the most well mixed type of mixture out there. A colloid would be the second most well mixed, and a suspension, well, that's not as well mixed. We can even take it a step further and look at something like trail mix, which is pretty easy to separate even just using your eye and your hand. Unlike pure substances, unlike compounds, mixtures don't exist in a set ratio. So you might have a mixture of trail mix with 2 cups of Rice Krispie Treat cereal and 2 cups of M&Ms and a cup of pecans because you don't like pecans as much. That's totally okay in a mixture. You don't have to have the same amount of everything. The next time you make that trail mix recipe, you might add only a cup of the cereal as opposed to 2. In a mixture, we see a constantly changing ratio. Now think back to those 3 types of mixtures we talked about a few slides ago. The solution, remember, we said was the most well mixed of our types of mixtures. It's a mix of 2 or more substances, and those substances are going to, at this point, because they're so well mixed, be uniformly dispersed. In other words, we're not going to find all of the sugar particles in a water-sugar solution in one part of the cup, and all the water particles in a water-sugar solution in the other part of the cup. They're going to be uniformly mixed together. They're going to be evenly spread apart in that glass. Solutions are going to look like just one substance. Think about salt water or sugar water. Looks just like the water, right? And in reality, a solution has 2 components to it. It has a solute, which is the substance that's dissolved, or that dissolves in the solvent. So in the case of sugar water, the solute would be the sugar. And a solution also has a solvent. The solvent is the substance that is doing the dissolving. So water is sometimes referred to as the universal solvent. That just means that it is really, really good at dissolving stuff. Other solutes you might encounter are salt. We think of salt water all the time. We think about some of the minerals and other substances that are dissolved into the plasma in our blood. Super important that water, or plasma in the case of our circulatory system, is able to carry those dissolved nutrients to the cells in our body. If we're thinking, bigger picture than that, this idea of solutions has applications across the board in physics and chemistry, in all sorts of disciplines of engineering. It's a big deal. But for the time being, just understanding what we need to of solutions, you can think of it in terms of salt water, with the salt being the solute and the solvent being the water. A practical example of a solution would be an alloy. That's a solution that is not liquid but solid at this case. And we have a metal and a nonmetal being, or a metal or a nonmetal, being dissolved into a metal. So there will always be a metal present in an alloy, but it might be mixed with another metal, or it might be mixed with something else. Alloys are intentionally created because they have properties that we love. Steel is an example of an alloy, and there are different recipes to make steel. Some are designed to increase the strength of the substances involved. Some are designed to make that end product rust resistant. But across the board, those alloys are finely tuned solutions designed to help us in some way as we're engineering. And then also, because mixtures don't have to exist in a set ratio, we see that the concentrations of solutes and solvents can change depending on our solution. Solubility is the amount of a substance that your solvent is able to hold. When we created those borax crystal ornaments back at Christmas time, we were creating a supersaturated solution. Basically what we did is we took our water, our solvent, and we put so much borax into it that the water couldn't dissolve it all. It dissolved as much as it could, and then with that solvent, or solute, that was left over, instead of dissolving because the solvent was full, the extra just settled out on the bottom, and we call all that extra stuff precipitate. Now a substance is able to hold, a solvent is able to hold more of a solute when it's warm. Those particles, if you think about that exercise we did in the classroom the other day where you became particles and moved faster the warmer you got, particles that have a high temperature have a lot of kinetic energy. They're able to move around one another with a bit more force. And because of that, they're able to take on more of a solute. they're able to hold on to more of something that's attempting to be dissolved. The minute that that solvent starts to cool down, it loses its ability to hold all that extra solute. And so when we created our borax crystal ornaments, we heated our water before adding the borax, understanding that when that water cooled down, it was going to have to let out some of the borax that it had dissolved. And those borax crystals, when they came out of solution because the water couldn't hold it anymore, they attached to our pipe cleaners. That's what made our ornaments look so nice. The second type of mixture that we see is called a colloid. This is a mixture with tiny particles. So now we are dealing with a substance that doesn't look uniform anymore. Salt water or sugar water just looks like water. A colloid has tiny particles dissolved or intermediate sized particles dissolved, and so we can see that they're there. Milk would be an example of a colloid. So would like Miracle Whip or mayo. Stick deodorant is an example of a colloid. These are substances where the particles are big enough to be seen, but small enough that they're not going to necessarily settle out if they're let to sit for a long period of time in their solution, or in their mixture rather. These particles are oftentimes large enough to scatter light. So if you were to look at a piece of Jell-O or look at a glass of milk through, or put it between you and a window, you would notice that that sunlight coming in from the window is distorted. Colloids are not able to be separated by filtration, so they're small enough that they can't really be separated out, but they're big enough that we can see them and they can scatter light. It's our in-between category for mixtures. Suspensions are the least well mixed of our three types of mixtures. These guys have particles that are so big that they will start to settle out if they're left for a long period of time. So the Pepto-Bismol that you see there on the screen is an example of a suspension. I don't know if you've ever used Pepto-Bismol before, but if you you probably know that you need to shake it before you use it. This is because those large particles start to settle out on the bottom if they're let to sit over time. Opposite our mixtures, we have pure substances. A pure substance is made up of only one kind of matter, and it has definite properties associated with it. Remember that we have two different categories of pure substances, the first being elements and the second being compounds. Now I know we're not getting a chance to watch these videos, so I will post them as separate links for you to watch if you would like on my website. An element is a pure substance that is unable to be broken down into other substances by any chemical means. Now there are only about 118 different elements in the world. They make up everything, but there are only about 118 initial elements that we start these combinations with. We only use about 30 to 40 of these 118 elements in our daily lives, so you can sort of guess from that that a number of them are quite rare. Elements are represented on the periodic table. They're organized in the periodic table, and we will talk far more about this organization later on, but for right now, just sort of understand that these elements are represented in short form by a symbol, and that could be either one or two letters. You'll see them in big print on the boxes of the periodic table. Now, compounds are also considered to be pure substances even though they're a combination of two or more elements. Now, the reason that a compound is different from a mixture is because unlike a mixture, which doesn't have to have a set ratio, in a compound we have the exact same number of elements combining in the same pattern or organization every time. So for instance, in water, which has a chemical formula of H2O, we are always going to have two elements of hydrogen bonded to one element of oxygen. If we took one of those hydrogen atoms out and it was just HO instead of H2O, now we have a totally different compound with totally different properties. Another example that's pretty well known is CO2, or carbon dioxide. Remember that the number after the O tells us how many of that element we have. So in the case of carbon dioxide, we have one carbon element, and we have two oxygen atoms, and we have two oxygen atoms, and those three elements are bonded together. If we were to take one of those oxygen atoms out, or if we were to put an extra carbon atom in and make it C2O2, now again we have a totally different compound with totally different properties.